machine learning. So what is machine learning? Machine learning can be conceived as a class of algorithms or methods or techniques that are based on data. It is a data-driven technique. By data, we mean records of past knowledge that we have about a problem, records of past experience that we have about a problem, and it is also based on the use of combination of computational techniques in the field of computer science, statistics, probability, and optimization. And to what end are we using the machine learning techniques is to be able to accurately predict the future vis-a-vis the previous knowledge that we have about the solution of a problem. That is basically what machine learning is all about. It's a data-driven techniques for the prediction of the future on the basis of the past. Now, why is machine learning necessary? You know, there is this hype about machine learning that it's the hot topic, the techniques that everybody is interested in using, but there are scenarios, there are situations where machine learning cannot be used. And one of the scenarios is when you don't have a data. Before you can use machine learning approach in solving any problem, a data must exist. And it is not just enough for you to have data, a pattern must exist in the data that you can learn from. Then when you have a problem and it is difficult to model that problem mathematically, then machine learning is the choice of technique to use to solve the problem. So when you don't have a data and a pattern does not exist in your data set, you cannot use machine learning. But the caveat is, even if you have mathematical model of a problem, of your problem, you can still use machine learning, but it will not be as efficient as you implementing your model mathematically. So why is machine learning necessary? Machine learning approach is necessary when you have data. It is necessary when a pattern or a trend exists in that data that you can learn from. Now, let's look at the advantages and disadvantages of machine learning. Machine learning, as we have said, is a data-driven technique. It can easily identify trends and patterns in huge data. The process of learning does not require human intervention. And the more data you have, the more the performance of your machine learning model. It can continuously improve on its own as your data grows. It has the capability of handling multi-dimensional and multivariate data. You can collect data from everywhere, and it has capability to integrate and aggregate your data and still use it to train its model. Of course, it has very wide applications, and which we are going to be looking at a few examples of the applications of machine learning. Now, what are the disadvantages? The number one challenge in the application of machine learning is data acquisition. The task of data acquisition is enormous. It involves a lot. And getting data correct, well-defined, well-characterized data is huge work, and that is still a challenge in the application of the field of machine learning. Because humans intervention is involved in the process of data characterization, then there is high error susceptibility. Now, also, there could be difficulty in interpreting results. And because it is data-driven and you require huge quantity of data, the computation cost is also very high. So it involves the use of high computation resources. Where is machine learning applicable? Machine learning techniques is applicable in the field of medical diagnosis, which is going to be the focus of this presentation. It's also applicable in the solving the problem that relates to automatic language translation, image recognition, speech recognition, traffic prediction, energy forecasting, weather forecasting, email, spam filtering, online fraud detection, autonomous vehicle control, robotics. The list continues, is inexhaustible. So machine learning has very wide range of applications. Now, next is, what are the types of machine learning? Basically, there are two types of machine learning: the supervised learning and the unsupervised learning. Reinforced learning is like a variant of the two. It's like the midpoint between supervised learning and unsupervised learning. Supervised learning involves data that have labels. The labels, the category or class of the data has been identified in the data. So that is it is in that situation that I can use supervised learning. Unsupervised learning involves data that has not been labeled. Reinforced learning, on the other hand, involve data that's not been labeled, but only a few of the data is labeled, and you are expected to figure out the rest of the label of the data. Now, in which learning problems do we apply supervised learning? Supervised learning is applied in classification problems. It is applied in regression problems. An example of classification problem includes medical diagnosis, which this presentation is going to focus on, image classification, fraud detection, email spam detection. Regression problem, example of that is energy forecasting, which involves being able to predict load demand in the power sector and all of that, vis-a-vis the weather, the situational circumstances upon which the load is demanded. Then under unsupervised learning, we have clustering, which is and dimensionality reduction. Example of a clustering problem is in the field of meteorology. And dimensionality reduction, we have speech recognition, image recognition, and text mining. For reinforced learning, this is applied in the field of control and automation, and as well as robotics. So these are the types of machine learning and the various areas of problems where they are applied. Now, our focus in this presentation is going to be on classification, solving classification problem, or what I will call diagnostic classification problem. And a lot of algorithms have been developed to solve some of these problems, and I've highlighted some of the examples here, which I will discuss very briefly before we move ahead. And one of the examples of classification algorithm is k-nearest neighbor. Another one is discriminant analysis, naive Bayes, support vector machines, ensemble methods, neural networks. For k-nearest neighbor, it operates or it works on the assumption that identical data points are close to each other. So KNN captures the idea of similarity between data points. Data points that are similar to each other are probably in the same class. So it is on this assumption that k-nearest neighbor works. Discriminant analysis is a method that finds the center of a class and look at data points and see, okay, which of these data points is close to the center of that class. So the distance between data points and the class, if it is low, then it is assumed that the data points belong to that class. Those that are far away from the center of that class will not belong to that class. Naive Bayes actually is on the basis of the Bayesian theorem. Now let's move on to support vector machines. This algorithm actually is most efficient when you are dealing with high-dimensional data space. It helps to find the best hyperplane that can help you classify your clusters into their various classes efficiently. And ensemble methods take advantage of combinations of learners, weak learners, and combine them to obtain a very strong learner that can be used to make an efficient or an improved performance prediction. Neural networks, on the other hand, apply weights and continuously adjust that weight to your data features until data with the same labels begin to yield similar outputs. And then you can begin to classify them according to the kind of outputs that has been yielded. So this is the much on examples of classification algorithm. Now, we want to define diagnostic classification problem. The first thing we need is input variables from our data set. And we are going to be looking at breast cancer data. The input variables are the features that have been extracted from the data that has been collected. These input features are also known as predictors. They are also referred to as attributes. And these features are represented by a symbol xi, and is a set of many features that are grouped together, like x1, x2, x3 up to xn is equal to xi. That x1 can be the cell radius of a cancer cell, x2 the cell perimeter, x3 the cell texture, and so on until you get to xn. That is the number of dimensions of your data set. So this is the definition of the input variables to your system. Now we go on to the output variable, which will be the diagnosis. We want to receive the inputs, process it with our algorithm, and be able to predict an output on the basis of the knowledge that we have, on the basis of the correlation of the input to the output. So our output variable is the diagnosis, and this is denoted by Y, and it can either be M or be a binary status. M is a malignant cancer and B is a benign cancer. Now, the output variable is also known as the response or target variable. So in order for us to properly define our classification problem, we need to define our input variable, that will be our data features, and also define our output variable, which will be our diagnosis, which is to be predicted. So the theoretical formulation here is that given an output response, which will be a binary diagnosis, benign or malignant, and given also the data features or predictors, which we have according to the characteristics of our data set, that will be xi, which is equal to x1, x2 up to xn. It is assumed that there is a correlation that exists between y and xi. And this is what I was referring to when I was saying that it is not enough for you to have data, but a pattern must exist in your data. There must be a trend. There must be something about the features that must suggest to us that this is the kind of diagnosis to expect. So this correlation is given by y is equal to f of x plus epsilon, where f is the unknown function of x1, x2, xi, and epsilon is the random error that is associated with the learning. So in this formulation, the function f is the hypothesis that represents the systematic information that x provides about y. What does this mean? It means that there are certain pointers, there are certain information that is embedded in the characterization of the features that will enable us to determine whether it is a benign cancer or it is a malignant cancer. And that is what the classification is all about. The unknown hypothesis F that connects or maps the input variable xi to the output variable y needs to be estimated. And that is what our algorithm is going to do. So machine learning refers to a set of approaches for estimating or approximating hypothesis F to predict Y accurately. Okay? So the goal of diagnostic classification, and the goal is to develop and train a machine learning model that can be used to predict that a cancer tissue sample is either malignant or benign for new patients based on the past record of cancer data with labeled diagnosis. In other words, we want to be able to predict, having trained our machine learning model with the knowledge of the data that we have. We want to be able to predict when we obtain a new cancer sample, tissue sample. We want to be able to predict on the basis of that experience that this sample is benign cancer and or it is malignant cancer. By benign, I mean it is healthy. And when it is malignant, it is unhealthy. Okay, that's our goal. And the learning approach. The learning approach, the stages involved is that we take a known diagnosis, which is benign or malignant sample. We learn the features from that data, from data that are relevant to the target diagnosis, that is either benign or malignant. We use the learning experience to predict diagnosis for out of sample data. That's what I've mentioned, that we get new patients, and we now use the learning experience to predict that, okay, this new sample, it is benign or it is malignant. Now, of course, we have to validate our results. So we validate the accuracy of our prediction, whether our prediction is accurate or it is not accurate. So this is a graphical view of machine learning solution to classification problem. Yes, our model is to be able to classify our data set into benign cancer or malignant cancers. The green circles, small circles there, is the benign cancer, while the red square circle is the malignant cancer. So, essentially, what the machine learning method is doing is to be able to divide this into clusters, and any new sample we have, if it is introduced, it will be able, if it falls on the red side, okay, we say that is malignant. If it falls on the green side, it is benign. If it falls on the red side, it is malignant. The first graph there is 2-dimensional, while the second graph is 3-dimensional. You could also have multi-dimensional up to 10, 50, 30 dimension, but that is not easily represented graphically. Now we move on to the methodology of machine learning development. Now, the first thing is data collection. This is very important. We need data, and the data must be collected properly. We also need to pre-process the data. We need to reduce dimension. That is the challenge, is a major challenge of what we call the curse of dimensionality, where you have very high dimension of features as against the number of data samples that you have. This can create major problem for the performance of your machine learning algorithm. Now we go ahead to model development, which is now using the data that you have collected, the data that you have pre-processed, and you have defined the features properly to train your model so that proper accurate prediction of diagnosis can be made. Then we go ahead to model evaluation, which is to predict, to validate the performance of our model. Now, let's go a little bit more into details regarding data collection. Now, data collection process involves the following. One is data curation, two is data characterization, third is data feature quantification. Now, data curation involves removal of noise, and like what I will call purification of your data, and removal of bad data points. And data characterization involves the extraction of features from the data that you have collected, and they are supposed to be relevant features that correlates to your output variable. Now, quantification of data is that we need to assign values to all these features. It is these values, numeric values, that we can manipulate, and statistical methods are used to quantify these features. In this presentation, we are going to be employing the Wisconsin Diagnostic Breast Cancer Dataset. This dataset has been collected and has gone through these stages of data collection, data curation, data characterization, and quantization and quantification. And that is what we are going to use as our experimental data. I will talk a little bit more about that. So the University of California Machine Learning Recipe is the host of the Wisconsin Diagnostic Breast Cancer. The data set consists of 569 samples of human breast tissues, which are collected through fine needle aspiration biopsy. Fine needle aspiration biopsy is a method for collecting breast cancer samples, tissue samples. And in the data set, 458 samples are benign, are labeled as benign, and 241 samples are labeled as malignant. Now, 65.5% are benign samples and 34.5% are malignant samples. That is what has been collected. That is what has been given to us as experimental data, and that is what we are going to use. We can as well collect our own, but for the purpose of this presentation, we'll use this experimental data. Now, this is the breast cancer image, a microscopic image that is collected through fine needle aspiration biopsy. The first one is the benign sample, what we can call the healthy sample. The second one is the malignant sample. You can see some form of regularity in the nucleus of the cells in the benign sample. And you see a lot of irregularity in the malignant breast cancer image. Now, what is done in the characterization of this is to take the cells, the nucleus, the cell nuclei, and do statistical measurements on each of them, like finding the radius of the cell, finding the perimeter of the cell, finding the texture, and finding the mean and the standard deviation and all of that for each of these samples, and characterize them and tabulate the values that have been obtained. So the Wisconsin cancer dataset has been is documented into an Excel worksheet or CSV, and it has 33 columns. The first column is the unique ID allotted to each patient to differentiate between them. The second column is the diagnosis, which is either malignant M or benign as B. The remaining 31 columns, which is column 3 to 33, has all the 10 value features which has been computed for each cell nucleus of the biopsy, of the image, microscopic image obtained from the biopsy. Now, from columns 3 to 33, the 10 value features are computed for each cell nucleus, include the radius, the texture, the perimeter, the area, the smoothness, the compactness, the concavity, the concave points, the symmetry, and the fractal dimensions. These are the times that are statistically manipulated, the quantities that are statistically manipulated and quantified and tabulated for us to use at our cancer dataset features. Now, this is a snapshot of the Excel version of the Wisconsin dataset. It has, the first column is the identification, which is the number assigned to each patient, a unique number. Then the second column is diagnosis, which could be malignant or benign. And that is what we have represented as, denoted as Y in our theoretical formulation. Then the radius mean is X1, one of the features, texture is X2, perimeter is X3, and so on until you get to Xn. Okay, so you will recall that our input variable is denoted by X subscript I, which is a set of X's that of features that has been our data has been characterized with. And X1 is the mean of cell radius, X2 is the mean of cell perimeter, X3 is the mean of cell texture. And our target diagnosis is Y. M, we can be binary output, M malignant or B benign cancer. So we go to data preprocessing. Before delving into that, I think I should try to define some terms, basic terms of machine learning, so that we can facilitate our understanding of what we are going to do next. Now, data examples. These are instances of cancer data set used for learning and evaluation. It's simply our records, all the records that we have in our data. Data features is what I explained earlier. These are the set of attributes, often represented as a vector associated to a data example. Labels. These are categories or classes designed to assign to data examples. And in our own case, for the purpose of our cancer data, it is either malignant or benign. Training samples. These are data examples used to train a learning algorithm. Test samples. These are data examples used to evaluate the performance of a learning algorithm. While validation samples, these are data examples used to tune the parameters of a learning algorithm. So feature selection. Feature selection is a very, very important pre-processing stage. In the event where we have very high dimension that can impact negatively on the performance of our machine learning algorithm, there is need. If features that have been extracted are too much, there is need for sometimes for us to reduce the dimension of the feature. So feature selection is used to reduce feature dimension for model performance improvement. Now, what are the factors that necessitated feature selection? Number one is what is called the cost of dimensionality. You have too much features as compared with the number of training samples. So when you have very high feature dimension compared with the number of training samples, then there is need for feature selection. When there is presence of irrelevant data features, there are sometimes data collectors. They characterize the data and just give features that are most irrelevant, features that do not provide any meaningful information about the output of the data. So there is a need to do away with irrelevant data features and select only data features that are relevant. Then again, you can have presence of redundant data features. Now, this also is not as if it's relevant. It's because whatever information these particular features are providing, other features are providing the same thing. So why do we need to have that redundancy? So the need to eliminate irrelevancies and the need to eliminate redundancies are very crucial to the performance of our machine learning algorithm. And that is what feature selection can help us to achieve. So why feature selection? Feature selection is employed to achieve the following. It helps us to achieve shorter training time. In other words, if our data dimension is reduced, the computation time for our analysis will also be reduced. It reduces overfitting problem, and it also improves accuracy of our prediction, accuracy improvement. So that means our prediction will be more accurate if we use only features that are significant, features that are important, features that have relevance. Okay, that is why feature selection process is required. Now, types of feature selection methods. We have filter method, we have wrapper method, and embedded method. Filter method is the basic one. It uses individual feature, the predictive power of individual feature to correlate with the target space, while wrapper method combine features to determine the predictive power. Embedded method combines the quality of both filter and wrapper methods. But in this presentation, we are focusing on wrapper method. So types of wrapper methods. Number one, we have subset selection, we have forward step selection, we have backward step selection. These are the types of wrapper method, but our focus will be on subset selection, which is exhaustive feature selection. So machine learning model development. Now, the learning model development has this flow. We have collected our data. We have used feature selection to pre-process the data by way of reducing the dimension of our features. Now, the next thing is now to fit our model with the data that we have, which has been trimmed down and streamlined, to make the prediction of our diagnosis. Then we go ahead to predictive model validation. We now have to validate or measure the accuracy of our prediction. So the algorithm for exhaustive feature selection is what is graphically displayed. We have a set of all variables, and we generate a subset of that. We use learning algorithm to test if the subset performed well, and that is what exhaustive feature selection is all about. And at the end of the day, we are able to generate a subset features that are most significant to the prediction, so that our performance can be optimal. And so we select a combination of subset of features. We feed the model with each possible combination of n features, then use the test error to evaluate model performance. Now, the flowchart, a simple basic flowchart for our learning model, is that we take training samples. I have earlier defined these training samples, and we use these training samples to train our algorithm, which is now in turn applied to new data that we have obtained from a new patient, and to determine whether that sample, the new sample, is malignant or it is benign, and as shown in the flowchart. Okay, so having done that, we need performance metrics. We need to measure the performance of our prediction, the accuracy of our prediction. And typically, in evaluating machine learning model, classification accuracy, sensitivity, specificity are the performance metrics used to measure the accuracy of our model. So confusion matrix is a matrix that is used to help compute all these validation metrics. And let me go ahead to try to explain a little further. Now, the basic terms associated with confusion matrix table include the following. Now, we need to count how many true positives, that is correct prediction of malignant cancer, that we have obtained in our prediction. We count true negatives, the correct prediction of benign cancer. We count false positive, which is incorrect prediction of malignant cancer, which is now known as type 1 error. Then we also count false negatives, which is also incorrect prediction of benign cancer, known as type 2 error. All these are computed together in our matrix as shown here, under in the, is it pink or red color text. And on the basis of that, our classification metrics are calculated. For classification accuracy, is the addition of true positive, true negative, false positive, and false negative. Then the sensitivity is true positive divided by the sum of true positive plus false negative. Specificity is true negative divided by the sum of true negative plus false positive. And precision is true positive divided by true positive, the sum of true positive and false positive. These are standard performance metrics that are used to evaluate the performance of our machine learning model. And here we will just highlight classification accuracy for the purpose of this presentation. Now, This is the model, this is the result that we have obtained. Having, okay, I think I should also mention that ensemble method is used to develop our algorithm. And this is used for our prediction, and this is the result that have been obtained. We use weak learners of random forest. And we generate a strong learner from it. We also reduce our features. We have a number of features here. We use different number of features and obtain the results of the performance as accuracy in percent. And we also try to compute the computation time, that how long it took for this analysis to be carried out. Now, for you will observe that the number of feature, when the number of feature is 17, we have 98.25% accuracy, which happen within 405 microseconds. Then, when the number of feature is 24, we have 98.24 accuracy, and the computation time is 461 microseconds. And these are the highest, and this is depicted in the result graph. And we can see the two peaks. 17, we have the 98, the peak here, and we also have another peak at 24. So, what is the significance of this result? When 17 features were selected, 17 relevant and significant features, the classification accuracy of 98.25 was obtained. When we also selected 24 significant features, classification accuracy of 98.24 was obtained. However, the computation times for the selected features of 17 and 24 are 405 microseconds and 434 microseconds respectively. Therefore, the best choice is 17 selected features, because the computation time is less and it also has higher classification accuracy out of all the features that we have selected. So in conclusion, breast cancer dataset was used to train the proposed diagnostics machine learning model. Exhaustive feature selection method was used to select the most significant data features. The performance of machine learning algorithm was enhanced when few selected features were used for training than when all the features were used. Hence, diagnostic analytics based on machine learning algorithms is a crucial solution to efficient clinical diagnosis of breast cancer. Thank you for your attention.